So in this unit, we're going to start by taking a look at the inverse trig functions. So last year back in Algebra 2, you guys studied inverses and how to find inverses. And just a reminder, graphically, when you graph a function and its inverse, they are reflections across the line y equals x. And if you remember algebraically how you find the inverse, you switch the x and the y in the equation and then you solve for y. Remember, for notation-wise, the way we represent a function notation for inverses is you'll see f raised to the negative first exponent of x. Remember, this does not mean you're going to take the reciprocal. It's not the same as 1 over f of x. So if you take a look at f of x equals x to the third, and if you wanted to find the inverse function, remember what you would do is you would switch the x and the y. So I'd rewrite this equation as x equals y to the third, and then I would take the cube root of both sides. So the cube root of x is my inverse function for x to the third. Graphically, remember when you graphed x to the third, remember you have those key points on the graph. You've got the -1, -1, 0, 0, 1, 1. So there's my graph of x to the third. So then when I go to sketch the cube root of x, I know that they have to be reflections over the line y equals x. So when I graph my cube root of x function, it's going to look something like this. I messed up. I should have swirled that a little bit more. But here's my inverse function. But remember, there are reflections over that line y equals x. Remember, you also studied last year a composition of functions and inverses. When you take a function and you do a composition with its inverse, that's going to be equal to x. So for example, if I take my inverse function, which I found to be the cube root of x, and I evaluate it, when I plug cube root of x into f of x, that's going to be the cube root of x cubed, which would give me just x. Remember, this is the only time composition of functions may be commutative. Again, this would also be equal to x. Again, if I take a look at the example I just did, if I take my function x to the third and I plug it into my inverse, I'm going to end up with just x. Remember, when we talk about inverse functions, the domain in f of x becomes the range of the inverse function. Remember, the range in f of x becomes the domain of your inverse function. Not all functions are going to have inverses. In order for an inverse to exist for a function, it's got to be a function that is 1 to 1. So again, in order for an inverse to exist, the function has to be 1 to 1. What that means, it not only has to pass that vertical line test. In other words, it's got to pass to make sure it's actually a function, but it also has to pass the horizontal line test. So the horizontal line test is what you use on a function to show that none of your y values repeat. So the horizontal line test, we use the horizontal line test can only intersect a graph at one time in order for a graph to be 1 to 1. Now, if a function is not 1 to 1, we can restrict the domain. And we can force it to be a 1 to 1 function. For example, f of x equals x squared. If you take a look at the graph of x squared, we know that it's just my quadratic function. It's the parent quadratic function with the vertex at the origin. And you can clearly see it's not a 1 to 1 function. Notice it would fail your horizontal line test. That horizontal line intersects the graph at more than one point. However, if I take my graph of x squared and I restrict the domain to be x values greater than or equal to 0, then notice now with that domain restriction, I've got the graph of x squared with a restricted domain, and notice it is now a 1 to 1 function. So I can find the inverse with this restricted domain. This is a concept we're going to have to use when we talk about your inverse sine, inverse cosine, and inverse tangent. These are all functions, but they're not 1 to 1. So therefore, we have to restrict the domains. in f of x in order for it to be a one-to-one function.